Okay, why don't we get started? So, as you know, there's an in-class midterm Wednesday, and I believe the TAs have posted extended office hours. Is that correct? That's correct? Yeah, okay. So that's all posted on the notice board. My books are always open notes. Now, I admit it's kind of awkward about when you have all your notes online, and I've never been quite sure what to do about this. So I don't know what to do about this. Print out what you need. You can bring as much material as you want. It's fine. And I have and we'll put a little no electronics policy in place, so please don't have cell phones. Cell phones that go off will be dealt with like that wonderful YouTube video I saw some time ago. You remember that? The guy, I forget where it was posted exactly. It was a video of a lecturer in front of a class. I think it looked like it was 60 Evans or something like that, and the cell phone went off, and the camera panned over. The lecturer went up to the student and said, hand it over, and then he threw it on the floor and stomped on it, and I thought that was great. Yeah, I know it was probably a setup, but still it was great. All right. I'll release the Project 2 spec today when I've finished proofreading it. And the files will follow in fairly short order after I finish with all the other stuff like tests and so forth that I have to do. And and that should be that. That should be kind of interesting, and I'm sure that you'll now. Those of you are not obligated to maintain the same teams as last time, but if you change, you must update the information. As you know, only you can remove yourself from a team, and only an existing team member can add someone to a team. If you need to do some other operation, like eliminate a team altogether or something like this, just let me know. We can do anything else that the interface doesn't let you do, at least once we make sure you're really authorized to do it. So that should be okay. And anything else? Questions? Administrative actions? Let's return to this. I haven't got, what's going on here? Why is this chopped off? This is really annoying. Is it chopped off because I'm over here, or is it? Oh, that's better. So, yeah, I have to get this installed on the instructional machines. These Europeans are just so used to giving us non-standard packages to install that it just becomes quite annoying sometimes. But there you go. What can you do? This is another example. I'm just talking about this language that we're going to use for other purposes in general terms, prologue, which, as I said, here I go again. I think I said at one point, I'm introducing to you now simply because I'm introducing that to you now because, well, in part because I think it's kind of interesting to look at new programming languages just to expand your mind a little bit. This particular one, again, is a declarative language, so-called, meaning that the idea is that rather than explicitly give the steps necessary to solve a problem, you give a definition of what it means for the problem to be solved, and the thing finds the solution for you. Now, because this so often involves exponential search, it doesn't actually work out that way. You end up defining the problem in such a way as to strongly suggest what the necessary algorithm is. But nevertheless, it's an interesting idea, and it's led to some interesting work. So here's another example in which I define two predicates, member and ordered. And the idea behind these things, member ordered and perm. So perm is supposed to capture the idea that X is a permutation of Y. And the way that we do this is that two empty lists, we declare facts about permutation of. One of them is that the empty list is a permutation of itself. And another one is that if you have two lists that aren't one of which is not empty, namely the second list is not empty, it starts with X and has S as its tail, then those two are permutations of each other, assuming that the first element of the second list is a member of Y, and the remaining elements of Y, member has a three-element relationship. It means the first element is a member of the second element, and the third element is are all the other members of the second element. So basically, this says that if the first element is in Y, and the remaining members are a permutation of the remaining members after S, then you have a permutation. That's a permutation. So then you have this definition of member, which says that X is a member of a list that starts with X, and the tail of that list is then the remaining elements. And otherwise, X is a member of if you have a list that starts with Y, and X is a member of the second is a member of the tail of that list, then that's fine, and then if R2 are the remaining elements, then you get then you can say that X is a member of R1 and R2 are the remaining elements. So you put these together, and then finally we have a definition of what it means to be ordered. A one element and a zero element lists are ordered. So remember that the uppercase variables again are sort of quantified over by everything. And we say that a list is ordered if the first two elements are ordered and all the rest of the list is ordered. So this is pretty straightforward. And the interesting thing about it is that, first of all, we get the same phenomenon we saw last time, which is, for example, that I can ask, what are the permutations of 1, 2, and 3? And I will get them. So I don't know what they are. What are they? And it will tell me that, 1, 2, 3 is such a permutation. And, I can't remember what and 1, 3, 2, it will basically go through, it will find all the permutations, all the things that match that rule. If I now ask, find me a permutation of X that is ordered. Suppose I ask for a permutation now of some elements, let's say 4, 0, 1, 2, and say 5. No, make it 3. And I ask for a permutation X of that element such that X is ordered. So such that ordered of X. Now, what this means is that it will find me, it will try to match this permutation, but this time it will be restricted by making sure that the permutation is ordered. What's this? What did it not like here? Yes, it does, doesn't it? I'm trying to figure out which syntax error. What have I done wrong this time? I not put in a space, perm ordered. Nope, I don't know what that is. I will have to figure out. This is what happens when you have online. Oh, I'm sorry. Yes, of course. How stupid of me. I've got it. I want to know. got this wrong. I want a list that's a permutation of 4, 2, 3 that is ordered. So I ask find me an X such that both of these are satisfied, and sure enough it does. If I then ask it for another one, it's done. So it does it. Now you can see where the problem is, because the way that it did this basically is that it did the same thing I did up here. Namely, it cycled through all the possible permutations until it found one that also satisfied ordered of X. So basically the algorithm is find something find a permutation that works, check to see if it's ordered. If not, fail, go back, find another permutation of X, check to see if it's ordered, and so forth. And as you know, this is a terrible sorting algorithm, but it sure is elegant. I mean, it's just amazing that you could actually write this and the thing works. I mean, that's very strange. And of course we have it's just, well, I don't know. I find it's so intrinsically fascinating that somehow I just thought you'd like to see it. So I thought I'd share it with you. All right. So this is sort of the basics of these. I think at this point it's probably a good idea to go back to regular lecturing here, if I may. So if we go back to, we're probably finished with this one now, aren't we? Okay. All right, so we have this business, databases. Right. So now we can use this as a basis for describing, or basically a notation for describing rules in a programming language, type rules in a programming language. Now, unfortunately, as I say, this is sort of a suggestive thing. There's no decent way of, first of all, the type system of our little piece of Prolog is not complicated enough to justify, or regular enough to justify the use of this. So I'm presenting it to you as a somewhat academic exercise, I confess. But it's a good way to perhaps train yourself to start thinking cleanly about specification problems like this. And for those of you who want to go on to become CS graduate students, well, you'll be seeing a lot more of this with a different notation in the future. So we have, this is just a few little notes on notation in case we need it. So how might this be useful to us? Well, here's an example. Or how might it be applicable to this course? Here's an example. Suppose I wish to write a rule that says that the type of E1, that talks about the types of addition. So I can write a rule that says the type of an expression. So basically what I'll say is, okay, we'll have expressions on one side, or we'll be talking about expressions. And we'll do this, we will use this predicate type of, we'll define it somehow, so that it means that the type of the first thing is the second. And then we can say things like E1 plus E2 has type int, assuming that both E1 and E2 have type int. And if one of them does not have type int, then this rule basically fails. So unless I have some backup rule, I'll presumably get some indication of a type error in this case. I can say that all integer literals have type int if I happen to have a predicate lying around, and there is a built-in predicate that allows me to tell whether a certain term is actually an integer literal. So what we can do is arrange this so that this type-off predicate works on all ASTs. We just have, I'm just using a convenient notation for ASTs. So Now, of course, when you do this, when you carry out this exercise, you can make mistakes. Here's an example. If x is an integer, then the type of x can be said to be any. It's legal to say that x is of type any. That's interesting, of course, but it's kind of silly. It's insufficiently general. If everything has the type any, then you could just write type x of any. That isn't quite true. It turns out that isn't quite true in our Python dialect, but it's close enough for the purposes of this lecture. So we can. The idea is basically that you can that you'd like to keep your rules as general and as simple as possible. So here are some examples from Java. I can say that the type of not x is always Boolean, assuming that the type of x is Boolean. I can say, let's see, what else do we have up here? The type of while. Well, while doesn't really have a type. It's type void. But in order for that expression to have a valid type of any kind, all its pieces have to have valid types too. So we check its pieces, and we say that the statement is validly typed and it has type void, assuming that the condition, the E condition, has type Boolean, and S is some statement that correctly types and has type void. Now, I'm using while ES here as I'm asking you to imagine that it's my representation in Prolog of the abstract syntax tree of the AST for while. Okay, that's pretty clear. I can say that X is of type void. In other words, it's legal to put, in Java, it's legal to put X in a place where you're expecting type void, as long as Y has as long as X has some type that's a value type, what we call a value type, such as int, double, Boolean, and so forth. So that means basically any expression that has a value you can use as a statement, which is what it's correctly typed if you use it as a statement. So you can, in other words, you're allowed to ignore a value. That's what that rule means. Well, now we have a little problem. Now, at this point, we run into a problem, which is that we have a difficulty with this kind of rule. So suppose that we have a variable, and I'd like to know, is it the case that that variable has type int? Now, there are several ways of dealing with this. One way to deal with it, the way that we use in our project, in fact, is that you can say, well, we don't actually, the first thing we're going to do is we're going to go through the program and we're going to figure out what the types of everything, what the declared types of everything are. We take an initial pass through the program and figure out the types of everything. And only then do we do this so that we would never ask the question, is X of type int? We would ask instead the question, is X, which by the way is demonstrated, is X decorated with the type int of type int? And it would say yes. So that would be the easy way to do it. Now the classical treatment in this, however, is suppose you don't want to do that. Suppose instead that you'd sort of like to do some of the you'd like to separate the variable names from the information about the variables. So we can use a little trick to do this. So here's the idea. I'm going to update my type of predicate so that it not only asks what's the thing that I'm trying to find the type of, and what's the type that I think it is, or what is its type, but also something else which says what is the environment, what are the meanings of variables at this point in the program, or what are the types of variables in this part of the program. So we'll just invent some sort of a concept of a type environment, which will be a mapping from identifiers to types. And that type environment is supposed to give the types of all the free variables. Free, by the way, this is a general term. Free is a term you'll see elsewhere. In any time you're talking about expressions, logic, things like this, programming languages, a free variable is one that is not defined. A variable is free, or an instance of a variable is free in some expression if it's not defined within that expression. So, for example, here, if I just have a variable x standing alone, well, obviously x is not defined in x. That's just x. There's no definition of it there. Therefore, x is what we call a free variable in that expression. Kind of a trivial example. In this lambda expression here, there is no definition of y, so y occurs free in this expression, but x does not. So x has a definition inside the lambda expression. We say that x is a bound variable. It is not a free variable. And then in this one here, here's a map thing where now this is a little bit tricky because here's an x. This x here is not free. It's bound to this x of the lambda. But this x over here, which is outside the lambda, this x is free. So the variables x, y, map, and g are free. Specifically, this is the free instance of x. This is the free instance of y. And this is the free instance of g. Right? And there is one other instance of x, but there are two other instances of x, but they are bound. So this is just terminology. So that when I say that something is free or bound in an expression, that's what I'm talking about. So what I can do in Prolog, I could model this in Prolog. Well, we could just say it in mathematics. If you're just writing mathematics, you just say, okay, fine, the type environment is a mapping from identifiers to types, end of story. If we were doing this in Prolog, you'd have to implement it. And here's an example of how you implement it. So this says, let's read this. It says that the definition of I is T. So the intention is that defin I, T, and something in environment means the definition of I is T in the environment, in that environment. So the definition of I is T if there's a little pair, def IT, somewhere at the head of that environment. Okay, that's kind of obvious. And otherwise, if that first identifier, the identifier of the first thing, is not I, then the definition of I is T if the definition of I is T in the remainder of the environment, everything except the first element. So, right, so now I just redo my type of predicates to always have this type environment. So now I can say, for example, that if T is a variable, I can ask whether T is what a variable's type is by simply including this rule that says that the type of I is T in that environment if I is defined to be T in the environment. Yeah. Okay, so that's kind of obvious. That takes care of the variables. And that means that my examples now look like this. The type of E1 plus E2 is an int in some environment, assuming that E1 is an int in that environment and E2 is an int in that environment, and so forth. So this is all, these are all kind of obvious extensions. We just pass the environment down and we get the rules we want. So now let's see where things get a little complicated. How do we deal with lambda? Well, this is actually something, this should feel kind of familiar because if you did the metacircular evaluator, you did something like this. Whether you know it or not, you did something like this. So what I want is So I want to type this lambda expression. Well, what's the type of a lambda? Well, the type of a lambda, assuming that we have only one, we're only dealing with one argument, lambdas here, is the type is a function type taking variable to taking a variable of some type to type t. That's what, because lambdas always evaluate to functions. And that's true assuming that E1 has type t, assuming that E1 has type t in the environment where x is a variable that has type any. So that's, if you contemplate this, this is everything is here. We have basically this says that if assuming we're allowed to evaluate t, we're allowed to evaluate E1. When we're evaluating E1 or when we're processing E1, we assume that x has the type any, and that if there is another definition of x someplace, if there was a definition of x in the original environment, well, then that doesn't count anymore, because the definition that's going to be found when you use the type of function is the definition you just added. So this basically takes care of it. And you should study this example, because if you understand it, you understand what the mechanism that's going on, the trick that's being used here to in Prolog to define, and also in other notations for the same thing, to define what it means to lambda bind a variable. Now, in our dialect, there would be an additional thing, because in our dialect you can also say lambda of x : some type E1. So lambda of x : some type. I should have had a slide with this on it. How would I change the rule then to make that work? So x : some type E1, meaning that's the type annotation that you can add in our language. What changes? Did I see? Yes. Go ahead. That's right. And one other thing. So you're right. We changed, instead of saying x any, it would be x whatever the defined type is. One other thing. Yeah.
You need to include the type of x in the argument.
No, that's what he said. So the type of x. So
then you'll have to change in the def of x, comma any in the environment. You would have to change that any to whatever type of x.
That is what he said. So that's how I interpret it. So if this were x : t1, then this any would change to a t1. What else would? There's one other change.
Oh, the any to t.
That's right. So now this lambda would now be a function mapping type t1 to t. Okay, I will insert a slide on this for the sake of you later going back and studying it, so that you can see what we're talking about here, because I admit it's a little bit awkward to do this here. Now, so in other years, they've taught this course in the past from time to time using a language called Cool that has a let clause, sort of basically like scheme let clause, except that it's typed. So I can say let x be of type t0 in E1, and that means that x is now a variable of type t0, and it's defined throughout E1. So you can use it as a variable everywhere in E1. And the value of this let expression is E1. And so it's very much like scheme, except that this is an uninitialized variable in this case. So if we assume that the AST for that is represented as let x t0 and e1 in Prolog, then we can just write essentially the same rule as we did before. And say, well, no, I'm sorry, shouldn't say that. A similar rule to what we wrote before, which is that that this whole let expression has the type T1, is correct and has the type T1 in this environment. Assuming that this expression here, E1, has that type T1, when you define x to be a variable of type T0. So it's very straightforward. So this is a note. Once you get used to it, the notation is kind of backwards, admittedly, but once you get used to it, it makes things reasonably clear. All right. Well, it's fruitful to turn to examples that don't work. But before we do that, I think I better take a break. So I think what I'm going to do after the break is I'll go through quickly go through one or two examples, and then I feel I ought to throw the floor open in case people are feeling sufficiently nervous about the midterm that they have a burning question that they need to ask that they can't put off to the bulletin board or something, or one of the office hours. And these questions, of course, will not include anything along the lines of, will X be on the test? To which the answer, of course, is always maybe. Okay, very good. Let's take a break. All right, let's start up again. So here's an example of typing gone wrong in a subtle way. Here's an obvious extension of the previous statement. This is an initialized let-like scheme. So I'd like to say the statement, the actual programming language statement is let x of type T0 be initialized to E0 in E1, and the result is the value of E1. Okay. So here's the putative type rule. I'll say that the type of all of this is T1 in some environment, assuming that E0, that is the initialization expression, is of type T0, right, the type of X, and the type of E1 is T1, assuming that X has that type, T0. So what's wrong with this rule? I mean, the rule is too conservative. That means by which I mean it rejects programs that are perfectly okay and that the compiler ought to know are perfectly okay. So, little exercise. From what you have understood about what this notation means, what is missing from this definition? Yeah. That's right. So in other words, it's possible that the type of E0 is actually some type T1 that's a subclass. It's not exactly T0. Now, actually, it turns out the problem here is that this rule could be right. It depends actually on how I end up defining type of. You can arrange things so that type of includes the notion of subtyping. But if you don't, if you take it to mean it is exactly this type, then you have to introduce an extra clause like this, for example. So the type of E0 is T2 in the environment, assuming that T2 is less than or equal to T0. We'll have to define what that means. That's not defined in Prolog precisely. And then that E1 then types properly. So we then have to go and define what we mean by one type being a subtype of another. But of course, that's just one more that's just one more definition. So this is a rule that allows us to have a little flexibility and look at the way that it works. We've introduced this variable T2. It doesn't exist anywhere up here. And it means basically, when we write this in Prolog, it means basically that a variable appearing for the first time on the right side means there exists, basically. You might ask yourself, why does it mean for all on one side and there exists on the other? Anyone know enough predicate logic to know why that's the case? Never mind, I'm sorry. It wasn't a serious question. All right, so we can deal with that particular conservative rule by writing it like this. And then, of course, it's always possible to screw things up entirely. And this is an example here that not only disallows legal ones, but it also allows incorrect ones. And the question is, what is the typo or mistake that I've made to cause this to not work? I guess I'd better make sure that I know what the typo or mistake is. Oh, yes. Or let me be more specific. Give me an example of a program that it rejects, or give me an example of an incorrect program that it says is okay. Yeah?
The type of E1 should be a subclass of C1?
So the class of, yes, actually that's very good. That's a possibility that we didn't consider in the last one, but that's correct. Actually, that's one example. And I should actually augment the slide with that. I was dealing with we dealt with the argument type, or the type E0, but there's also the fact, there's also this question of what is the result type. Well, there are various ways of doing it. So you could do that, yes, if your definition of type is a subtype of, includes is a subtype of, rather than is exactly that type. You could perhaps do that, but I'm seeing a couple of other errors as well. Anyone else? This is actually pretty glaring, frankly. Okay, I'm seeing the same. Oh, yes, go ahead. Right, so what is that going to do? What's the result going to be? That's right. It's as if I'll get the result, I'll get the answer as if, the same answer as if E1 had been evaluated without the variable x being defined. And that could be wrong. I mean, it could either be necessary that x have the type T0 in order to make sense of E1, or it could give me the wrong result. It could say, for example, if the expression E1 was simply x, then this would give me the type that x had in the outer environment instead of the type T0. So yes, this is really a fairly screwed up example. All right, there are more things to do, but I think at this point I'm going to ask if somebody has a burning question related to the midterm or material that we've covered, I'd be happy to answer it. If not, we can. God, I am so in awe of your grasp of the material. I look forward to the high scores that I expect to see on this test. All right, very good. Well, then we'll see you Wednesday.